Hi, this is Aryan from EDD Academy, and today we're going to be going over motion along a line. So let's start with the three important functions for this unit: position, velocity, and acceleration. These are all functions of time, which means they input time and output their respective values. And this applies to a particle on a one-dimensional line. So what the position function tells you is where on the line the particle is. The velocity function tells you how fast it's moving and in what direction. And acceleration tells you how fast the velocity is changing. Let's look at an example. So if I arbitrarily declare this point to be 0, and say that I have a particle at time equals 0, at point 0, then at time equals 1, it moves to point 1, and at time equals 2, it moves to point 4. Then I could say that x of t, which is a function that inputs time and returns the position, is probably equal to t squared. And this is the notation we use, where x of t denotes position, v of t denotes velocity, and a of t denotes acceleration. And the two major equalities you're going to want to know for this unit are that v of t equals the first derivative of x of t, and that a of t equals the first derivative of v of t, which is the second derivative of x of t. So here's some important facts you'll also want to know. So for position, negative is left on the number line. This is pretty intuitive. If this is 0 and this is 1, then this would be -1 and so on and so forth. But for velocity, negative means you're going leftward on the number line. So if at t equals 1, I'm here at point 4, and at t equals 2, I'm here at point 3, I moved leftward. Therefore, my velocity is negative. And this is regardless of the fact that I'm in the positive domain of the number line. That just doesn't matter. Two other major facts you're going to want to know are that acceleration and velocity, when they have the same sign, the particle is speeding up. And when they have different signs, the particle is slowing down. Let's take a look at a sample problem. Here we have the function x of t equals 2t cubed minus 4t squared plus 3t minus 1. First, we're going to do an algebraic problem. We're going to find the average rate of change of x of t from t equals 1 to t equals 3. So let's do that. This is pretty simple. It's just x of 3 minus x of 1 over 3 minus 1, or 26 minus 0 over 2, which is just 13. And this is accurate because it's the slope of the secant line of x of t from t equals 1 to t equals 3, which is a pretty good approximation of the tangent line at t equals 2. So let's do that. Let's calculate the tangent line by finding the velocity at t equals 2. So, of course, v of t is just the first derivative of x of t, which equals, let's see here, 6t squared minus 8t plus 3, evaluated at t equals 2. If we do the algebra, that is 6 times 2 squared minus 8 times 2 plus 3, which is 11. Pretty close to our original 13 that we got for the secant line. This is confirmed by the fact that the point 2, 11 is on our velocity curve, which is just the first derivative of the position curve. Now let's find the acceleration at point t equals 2. So here we have acceleration, which is of course just the first derivative of velocity, and that is 12t minus 8. Of course, evaluated at t equals 2. We do the algebra, that is 12 times 2 minus 8, or 16. And this is confirmed by the fact that the point 216 is on our acceleration curve, which is again just the first derivative of the velocity curve and the second derivative of the position curve. Let's do another slightly harder problem. So here we have our position function x of t defined by t squared sine t, and we're going to find the velocity, acceleration, and whether the particle is speeding up or slowing down at the time t equals 2 pi. First, let's take a look at what the function looks like graphically. Here we can see it is a periodic function that gradually increases in amplitude. Alright, so now let's find the velocity. Of course, the velocity is just the first derivative of the position. So that is 2t sine t plus t squared cosine t, evaluated at t equals 2 pi. If we do the algebra, this is 2 times 2 pi times the sine of 2 pi, which is, and then plus 2 pi squared cosine of 2 pi. Now we can use our trig here. We know that sine of 2 pi is just 0, and cosine of 2 pi is just 1. This means that we can ignore the 2 times 2 pi and only focus on the 2 pi squared, which tells us that the final answer is 4 pi squared. And just to help you visualize, this is the graph of the velocity function for our particle. Now let's look at acceleration. Here, acceleration equals the first derivative of velocity, as always, which is 2 sine t plus 2t cosine t plus 2t cosine t minus t squared sine t. And this can be simplified quite a bit by grouping like terms. So we have 2 minus t squared sine t plus 4t cosine t, evaluated at t equals 2 pi. And once more, we can use trig. We know that sine of 2 pi is 0, and cosine of 2 pi is 1. So we're really only looking at 4 times t. 4 times 2 pi is just 8 pi. And that's our acceleration. Here's the graph of the acceleration to help visualize that. And now we want to know if the particle is speeding up or slowing down. So if you recall, a particle is speeding up if the velocity and acceleration have the same sign at that point in time, and slowing down if they have different signs. So here, 8 pi and 4 pi squared are both greater than 0, so we can say that our particle is in fact speeding up. So now we're going to be looking at a graphical problem where we have the curve for the velocity function, and we want to know if the particle is speeding up or slowing down at all of these time points. So let's start with time t equals 1, right? As we can see, the velocity function is positive because it's above the x-axis, so v is greater than 0. But what about acceleration? Well, acceleration is just the first derivative of velocity, so because the function is increasing and therefore has a positive slope of the tangent line, acceleration is also greater than 0, which tells us that because these have the same sign, the particle is speeding up. Now let's look at t equals 3. Here, the velocity is negative because it is below the x-axis, and the acceleration is also negative because, once more, the slope of the tangent line is negative because the velocity function is decreasing. And because these have the same sign, even if it's negative, the particle is speeding up at time t equals 3. Now let's look at time t equals 5. Here, again, the velocity is less than 0 because it is below the x-axis. But what about the acceleration? The acceleration is positive because that's the slope of the tangent line, because the function is increasing. So a is greater than 0. This means that the particle is slowing down because velocity and acceleration have different signs. Now, t equals 0 is a unique case. Very clearly, the velocity is less than 0 again. But what about the acceleration? Well, the slope of the tangent line is 0. So the acceleration must also be 2. What does this mean for whether the particle is speeding up or slowing down? Well, it means it's doing neither at that point in time. It's pretty straightforward. Now let's move on to a slightly more time-consuming problem. Here, instead of giving you a graph, I have given you a function definition. And based off of this, I want you to tell me if the particle is speeding up or slowing down at the following times. So the way I would go about doing this is, first I would determine the velocity function definition and the acceleration function definition. Then I would plug in all the time points to figure out whether it is speeding up or slowing down at those particular times to both the velocity and acceleration functions. So let's do that. First of all, we know that velocity is the first derivative of position. So that is 14t plus 2 sine t plus 2t cosine t minus 2e to the t. And now let's look at acceleration. Acceleration is just the first derivative of velocity, of course. So that would make it 14 plus 2 cosine t plus another 2 cosine t minus 2t sine t minus 2e to the t. And we can simplify this a bit more by combining our like terms. So we get acceleration is equal to 14 plus 4 cosine t minus 2t sine t minus 2e to the t. All right, now let's plug in our time values to these two equations. So v of 1 is 14 times 1 plus 2 sine of 1 plus 2 times 1 times cosine of 1 minus 2e to the 1. And if you plug that into your calculator, you should get approximately 11.33. Now a of 1 is 14 plus 4 cosine of 1 minus 2 times 1 sine of 1 minus 2e to the 1. And if you plug that into your calculator, you should get roughly 9.04. And because both 11.33 and 9.04 are greater than 0, we can say that at time t equals 1, the particle is speeding up. And now let's look at time t equals 2. So first we're going to take v of 2, which is 14 times 2 plus 2 sine of 2 plus 2 times 2 cosine of 2 minus 2e to the 2. And this is approximately 13.38. And now let's look at the acceleration at time t equals 2. This is equal to 14 plus 4 cosine of 2 minus 2 times 2 sine of 2 minus 2e to the 2. And this is about negative 6.08. And because 13.38 and negative 6.08 have different signs, the particle is, in fact, slowing down at time t equals 2. Oops. All right, now let's look at, finally, time t equals 3. First of all, v of 3 is 14 times 3 plus 2 sine of 3 plus 2 times 3 cosine of 3 minus 2e to the 3. And this is approximately negative 3.83. And now let's look at a of 3, which is 14 plus 4 cosine of 3 minus 2 times 3, fix that 2, sine of 3 minus 2e to the 3. And this is approximately negative 30, negative 30.98 if you plug that into a calculator. So now that we know that both of these have a negative sign, we can say that the particle is speeding up at time t equals 3. And just to help you visualize all this, here is the graph of the position of the particle in black, of the velocity of the particle in red, and the acceleration in blue. As you can see, the points roughly match up with what we got, and that is all for the lecture.